Welcome to Maths with EJD. In this video, we still continue with numerical analysis and our focus turns to eigenvalues and eigenvectors. Under the matrices playlist, I've already talked about eigenvalues and eigenvectors very deeply. So what I'll be doing here is just to touch on it a little bit and to emphasize the numerical aspect of it. So let's move on. Eigenvalues and eigenvectors arise in linear algebra when studying how matrices act on vectors. Okay. Um, so given a square matrix, a square on the matrix playlists, I mean, you'd see everything about matrices. They're like what a square matrix is and all of that. So given a square matrix A, of course, a square matrix is simply a matrix with equal number of rows and columns, basically. So given a square matrix A, an eigenvector, an eigenvector V is a non-zero vector. It's a non-zero vector that only scales, that only scales when multiplied by A. It scales when multiplied by A rather than changing direction. So what that simply means is that we have matrix A multiplied by eigenvector V equals lambda V, okay? Where lambda is the corresponding eigenvalue. Lambda is the corresponding eigenvalue. So that eigenvalue is what scales it. It is the corresponding eigenvalue. Okay, so that's basically that. Again, if you want the in-depth understanding of this, please head over to the matrices playlist. That was my first playlist on this channel. So let's look at this example. Consider the matrix A, which is which is 2, 1, 1, 2, 2, 1, 1, 2, to find eigenvalues, to find eigenvalues, you know, from what we have up there, right? We have AV equals lambda V. So AV equals lambda V. That simply implies that we have AV minus lambda V equals 0. If you factorize V, which is common to both, so it means we have A minus lambda. Since we are dealing with matrices now, A minus lambda I. So I is the unit matrix. So that's A minus lambda I into V equals 0. So since V is the eigenvector, we can actually extract this, and then we have that the absolute value of A minus lambda I is equal to 0. So with this, we can actually find the eigenvalues, okay? So to find the eigenvalues, we can just take the determinant of this part and equate to 0. So that simply means we have absolute value of what was the matrix again? 1 to 2, 2, 1, 1, 2. So we have 2, 1, 1, 2 minus um minus lambda into I is a unit vector. Two, since we are dealing with a 2 by 2 matrix, so we are going to have 1, 0, 0, 1. So the principal diagonal has elements 1 all through, and this is equal to 0. So that means that we have absolute value of 2, 1, 1, 2 minus, lambda multiplying each element, that's lambda 0, 0, lambda. Okay, and all of that, the determinant is 0. And then we take the determinant of, so that we have the determinant of 2 minus lambda, that's 2 minus lambda. 1 minus 0, that's 1. Then 1 minus 0 is another 1. 2 minus lambda is another 2 minus lambda, and that is equal to 0. So with this now, we can take the determinant. The determinant simply means multiplying, we multiply this and subtract this. Okay, multiply this, the elements on the principal diagonal, and subtract the elements on the other diagonal. So that means we're going to have 2 minus lambda into 2 minus lambda minus 1, and that is equal to, okay, minus 1 times 1, right? Just to be perfectionistic. Minus 1 equals 0. So we can multiply now. 2 times 2 is 4. 2 times minus lambda, that's minus 2 lambda. Minus lambda times 2, that's minus 2 lambda again. Minus lambda times minus lambda, that's plus lambda squared. Minus 1 equals 0. So now we can tidy things up, and we have lambda squared minus 2 lambda minus 2 lambda, that's minus 4 lambda. 4 minus 1 is 3 equals 0. So we can actually factorize. To factorize this, right, we need two numbers which when multiplied will give us, so two numbers, when you multiply, you get the product of 1, which is the coefficient of lambda squared, and 3. So, which is 3. Two numbers you multiply to get 3, and two numbers you will add to get minus 4 that is in the center. Okay, that is what we should be looking for. In that case now, it means we can go ahead and talk about that as so the two numbers, so the two numbers have to be a product of 3, right? So that's simply 3 times 1. So 3 times 1 is 3. But because we have minus 4 in the center, so it means we need to have like minus 3 minus 1. So it has to be minus 3 minus 1. So minus 3 times minus 1 is 3. Minus 3 minus 1 is 4. Is minus 4 actually. So with that now we can progress and have lambda. So that can now be lambda squared minus 3 lambda minus lambda plus 3 equals 0. Okay. So now we have lambda. We can group, right? So we have lambda squared minus 3 lambda minus lambda, because minus is outside and we have introduced bracket. This has to be minus now, and that is equal to 3. So having groups, so the next thing we can factorize. So lambda is common in this first case. So we have lambda into lambda minus 3 minus 1 into lambda minus 3 equals 0. And that means we have lambda minus 3 into lambda minus 1 equals 0. So all this simply means that lambda 1 is equal to 3 and lambda 2 is equal to 1. That's if you equate this. Let me not jump. Right, so this is lambda minus 3 equals 0, or lambda minus 1 equals 0. So we have two possible lambdas. So if we call this one first lambda and call this one second lambda, that means we have lambda 1 equals 3 and lambda 2 equals 1. So, so the eigenvalues are 3 and 1. The eigenvalues of that matrix are 3 and 1. So we also need the eigenvectors, right? And this is how we proceed for that. To get the eigenvectors, remember where we started from. We had a v to be equal to lambda v. That means av minus lambda v equals 0. If you factorize v, which is the eigenvector, right? So we have a minus lambda I into v equals 0. So that's basically what we have. So this v now is what we are looking for as eigenvector. So if you remember what we also had up there, so this is now more like okay, so a minus lambda I, if you remember, it's basically the matrix A, which is 2, 1, 1, 2. okay, minus lambda I, which we already know is lambda 0, 0, lambda, okay. Then we have V, which we are actually looking for right now. So since everything is in terms of matrix, we can have V to be X, Y, okay? So now we are saying V is equal to X, Y. Those are the eigenfunctions. And this is equal to 0. So 0 now will also be a vector, 0, 0 like that. So if we go ahead, it means we have 2 minus lambda, 1, 1, 2 minus lambda, then into xy, and that is equal to 0, 0. So we have to now take the values one after the other. So, we have two values of lambda. Lambda is 3, lambda is 1. So we can say that for lambda equals 3, so we have 2 minus 3, 1, 1, 2 minus 3 into xy equals 0, 0. That means we have minus 1, 1, 1 minus 1 into x comma y, and that is equal to 0, 0. Okay. So in that case, if we do this matrix, I mean, the matrix multiplication, this is how that goes. You have, so you have xy, that's, that column. So you can write it twice. So you have xy, xy. Why are we doing it twice? Because we have two rows here. So you write it twice. Having written it twice, then you see the other part is this one. You invert it over the first one. That's minus 1, 1. Then the second one also, or let me color code that for effect. So you have 1 minus 1. So you have 1 minus 1 here. So all this now is equal to 0, 0. Okay. So that up there you have minus x plus y. So you have minus x plus y. Then here you have x minus y. All this equals 0, 0. Okay. So that you see that you have minus x plus y equals 0. That implies that y is equal to x, meaning that x is equal to y. So, of course, the other equation is just going to be exactly the same. So you have x minus y also equals 0. That implies that x is equal to y. So you see that they are both in ratio 1 to 1, right? So they are both in ratio 1 to 1. So that simply means that I'm trying to look for a very nice way of saying it. Yeah, from here, there's x equals y. Okay, if we I'm trying to see. Okay, yeah. So we have this, right? X is equal to y. X is equal to y. So x is equal to y simply means that they are in ratio 1 to 1. So see that this always gives x equals y. So an eigenvector is v1, which is equal to 1, 1. What that means is that if you take x to be 1, if x is 1, y is automatically 1 too. So that's why we have eigenvector there to be 1, 1. So then we go ahead for the second lambda too. The other one is where lambda is equal to, lambda 1 is 3. So we go for lambda 2, which is equal to 1. So we can jump to this same place. We can jump to this place. That's 2 minus 1. So we have 2 minus 1, 0. Oh, is it? Yeah, that should be 1. 2 minus 1, 1. Then 1, 2 minus 1 again. 2 minus 1 into xy. Then 0, 0. So that we have we have a matrix 1, 1, 1, 1 into x comma y equals 0, comma 0, 0. X, Y, 0, 0, right? So again, we can have just like what we did before. This is XY. So we have XY twice, XY twice, twice because we have two rows here, right, actually. So, and then this is 1, 1. So it comes over here. And then this is another, this is 1, 1 again. So the 1, 1 comes here. And all of this is equal to 0, 0. So we can just have x plus y equals 0, another x plus y equals 0. So it's the same thing pretty much. So for either one, x is equal to minus y. So that means that if x is equal to minus 1, then if x is equal to 1, then y will be minus 1. That's what that is. So this gives x equals minus y. So an eigenvector is v2, which is equal to 1 minus 1. Okay. So with all of this now, we can conclude that thus A, which is equal to 1, 2, 2, 1, I believe. Yeah, 2, 1, 1, 2. All right. Has what we call eigenpairs. So eigenpairs are the collection of eigenvalues and eigenvectors together. So thus A, which is 2, 1, 1, 2, has eigenpairs 3, 1, 1. Okay. And 1, 1, minus 1. So these are eigenpairs now. So the eigenvalue together with the eigenvectors. So showing how eigenvectors capture the intrinsic transformation structure of matrices. Transformation structure of matrices. Now, what we have done here is really important because if you remember, to solve systems of linear equation, for instance, we have to transform into matrices. So we have matrices as an underlying structure of most of these things. Even in programming, right? Matrices are really important because they help us to capture they help us to capture problems in a very nice way for handling, right? And that's why this is important. So with this, I come to the end of this video, trying to refresh our memory about eigenvalues and eigenvectors, which I've dealt with in at a very deeply in the first playlist as far as matrices are concerned. So you want to check all of that and see other things about eigenvalues and eigenvectors. So after now, I'll be talking about I'll be talking about power method for finding the dominant eigenvalue. So there's something called a dominant eigenvalue. So watch out for that video. If you have subscribed, thank you so much for that. If you have not, go ahead and do that right now and hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know how helpful this video is, and let me know if there's a topic you'd like me to teach you, a problem you'd like me to solve. Then like and share so that more people can have access to this great learning. Till I come your way again, keep doing maths right. Bye.